Okay, here is where we left off, guys. So we're on average acceleration still. So this says that a car is starting from rest and accelerates to a velocity of 20 meters per second due east in a time of 5 seconds. So how do we find the average velocity? So that's just taking final velocity minus initial velocity over time. So now we can just plug it in. Well, what was our final velocity? Well, it went to 20 meters per second. Our initial velocity, it said it started from rest. So that's just 0. And it did it in 5 seconds. So now on your calculator, just do 20 divided by 5, and you end up with 4 meters per second squared. That's it. I think that there is an example, that's why I have a blank slide here. So if you are in the textbook with me, go to page 26, and this is example 2.3. So it says, the driver of a car steps on the brakes and the velocity drops from 30 meters per second to 10 meters per second in a time of 4 seconds. So what's the initial velocity here? Well, it was initially going 30 meters per second, and it says east, which is just another way of saying that it was positive. The final velocity was that it was going 10 meters per second, and it did this in 4 seconds. So it wants us to find the acceleration. So just remember, final minus initial over time. So the final was 10, the initial was 30, and it did all of this in 4 seconds. Okay, so now take your calculator, do 10 minus 30 divided by 4, and that gives you negative 5 meters per second squared. Another thing that I need to kind of tell you about significant figures, because we kind of talked about that in the last video, is that you have to use whatever the least amount is that what they've used in the problem. So they used 30 and 10 and 4.0. So how many significant figures are all of those numbers? Well, they're all 2 significant figures. So my answer, even though in the calculator would have been negative 5, I need to make it 2 significant figures. So I had to add that decimal and a 0 after. Okay, so the homework kind of gets a little bit, it gets a little bit picky on some of that stuff. So see, this negative 5 meters per second squared is just another way of saying 5 meters per second squared west. Either way, okay? All right, so instantaneous acceleration, that's the acceleration at an exact time, just like we had instantaneous velocity. And that's a rate at which velocity is changing in time. Okay, so then we get to graphing. Okay, so a lot of people tend to not like graphing when they get into my class because they haven't had to do a lot of it in high school, or it's been a long time. So hopefully this is a little bit of a review for you, but if not, hopefully all of this seems to make pretty good sense. And when you've gone to math class and they've made you do things like slope, okay, well this is why. So again, comes back to that physics is the actual reason why you're doing the math. So you can see in this table, we've got a time versus position. And so we're gonna plot these on a position or distance versus time graph. So it's taken this data right here, I believe, and it's plotted it on this graph. So let's just look at the first one. Well, the first one's 0, 0, so that's easy. The second one's 5 seconds at 4.1 centimeters. So at around 5 seconds, because see, this would be 10, it's about 4.1 centimeters, and so on and so on. So if you were to connect those dots, you get sort of this straight up slope. And then you get to this 20, and it has like a straight line across. So there's absolutely no slope at all there. Then once you get to 30 seconds, it goes at a slope again. And then what happens? It goes down. But is it still a slope? Yeah, it just has a negative slope then. So if I was to take the slope of this line right here, I could pick any 2 points on here that I wanted to. Say I picked this one and this one, and I could find the slope of that line. Well, if I found the slope of it, then I would find the velocity, because this is a distance versus time graph. So I think it's going to have us do this here in a minute. All right, so this says that the graph is displaying information, and it's wanting us to answer some of these questions. All right, so it says, when is the car moving the fastest? When is the car moving the slowest? When is the car not moving at all? And at what time does the car start moving in the opposite direction? All right, so some of these things you might just be able to look at the graph and answer some of these questions. But basically, the steeper the slope, the faster the car is moving. So where does it look like it's going the fastest? Well, it looks like it's the steepest from 0 to 20 seconds, right? So from 0 to 20 seconds, it's going the fastest. Well, where does it look like it's going the slowest? I would say from maybe 30 seconds over here to 50 seconds. Or you could say too, well, when it's just this sort of constant, right? When it's constant like that, from 20 to 30 seconds, is it even moving? No, because it's not going any distance in from 20 to 30 seconds. So these you could kind of say are the same. So 20 to 30, obviously it's going the slowest. Or you could say from 30 to 50 seconds, it was going slower, than it was initially here. And at what time does the car start to move in the opposite direction? Well, the slope is negative from 50 seconds here to 60 seconds. So that would imply that the velocity is negative. So at those points right there, 50 to 60 seconds. So let's say, for instance, that you wanted to show that. Well, we're going to have to kind of approximate here. But I'm going to do like, let's say, this point and this point. So at 15 centimeters and 5 centimeters over, let's say like 18 seconds minus 4 seconds. Oh wait, that was really about 9 seconds, wasn't it? Because this is 10 right here. So if I take 15 minus 5 divided by 18 minus 9, I get about 1.11 centimeters per second. So it's kind of like meters per second, only not, right? But it's similar too. So those are units for velocity. Then we have from 20 seconds to 30 seconds where there's absolutely no slope at all. So that would just be 0 centimeters per second right there. Then let's see if we did like right there and right there. So we have 25 centimeters minus 15 centimeters. And we have over 50 seconds minus 30 seconds. So 25 minus 15 divided by 20, essentially. that's 0.5 centimeters per second. Okay, well, is that number right there less than 1.11? Yeah, so that's what we said earlier. When is the car moving the fastest? Well, from 0 to 20 seconds, because it has a bigger slope, okay? And then it says at what time does the car start moving in the opposite direction? So then if we go to this, these 2 points here, our final is now 20 centimeters, but our initial right here was 25 centimeters. And then we have 60 seconds minus, 50 seconds? So if you do 20 minus 25 divided by 10, you get negative 0.5 centimeters per second. So it has a negative slope, and that indicates that the velocity would be negative, and so therefore it would have changed direction. Okay, and it kind of shows you, it kind of like goes through all of that I just said in all of these slides now, so I'm not going to repeat necessarily all of that, but I want to get it to this slide because it does a distance versus time graph. So you've got distance versus time graph, and then it shows you what it would look like if you put it on a velocity versus time graph. Okay, so if we were to do the slope here again, then we could find a value, and that is a constant velocity from 0 to 20 seconds. Okay, so for whatever you found the slope to be, is going to be on the velocity, the y-axis. And then of course the time just stays the same, so 0 to 20 seconds. Well, from 20 to 30 seconds, we had no slope at all, so 0 velocity. And then once we did the slope for this point, it was about half what we found that first one to be. And then when we did this third or fourth, I guess, section here, we had a negative slope or a negative velocity from when it changed directions. All right, so let's answer some of these questions really quick. See how we do. All right, this shows a position of a car with respect to time. And it says, does the car ever go backward? And so, again, we have distance versus time. Well, what did we do? What happened when we had this segment right here? We had a negative slope, which meant that it did what? That it changed directions, right? So, if you go to this next slide, it says, yes, the distance traveled is decreasing during the third segment. I don't think it gave you the answers in all of them. I don't know why I did on that one. Okay. Is the instantaneous velocity at point A greater or less than that at point B? So look at the slope. Which one is a bigger slope? Is it this one or is it this one? At point A, by the way. Is it greater or less than that at point B? It's greater than. Yeah, see, I don't give you the answers from that one. So here we've got, in this graph, is the velocity constant for any time interval? Well, does it look like it's constant at any time interval? Yeah, it's this constant velocity between 0 and 2 seconds. Oh, now on this next one, it says, during which time interval is the acceleration greatest? So just the same way as we had with a distance versus time graph, we can do a velocity versus time graph, find the slope, and that would give us the acceleration. So at which point is there a steeper slope? Well, between 2 and 4 seconds. So it has the greater acceleration. This shows that a car is moving along a straight road as shown in the velocity versus time graph below. Does it ever go backward? Assume no U-turn. So this is different because it's a velocity versus time graph. Okay, so as far as velocity is concerned, does anything go below the 0 point here? See, like this is your X and your Y. You know, if we were to do a whole 4 coordinate system, is there anything in this below part? No. So that means that it never has a negative velocity like that. Okay, what about this one? This says, at which point is the magnitude of the acceleration the greatest? So, where do you think that there is a steeper slope? Well, it looks like it's at point A, right? Because there's a steeper slope there. There's no slope here and not quite as much at this point. This one, during which time interval is the distance traveled by the car the greatest? Okay, so this is asking us to find distance. We have velocity versus time graph. In order to find the distance, it's kind of like going backwards. So this is where you would have to do the area under the curve. Well, how do you do the area of a triangle? Do you guys remember? Area of a triangle. That's 1/2 base times height. So if I were to do that, I would do 1/2 2 times, let's just make up a number here, let's say 2. So that's 4 times 1/2, which is 2. How do you do the area under like a rectangle? Well, that's just length times width. So 2 times 4, essentially. Or sorry, 2 times 2. Length, or let's say width, length, it doesn't really matter. But you've got 2 to 4, so 2 seconds times 2 meters per second. Let me go ahead and put the seconds on there. So that would give you 4. What would happen to the seconds here? They would cancel and you'd be left with meters. So between 2 and 4 seconds is going to have your biggest area under the curve. And so therefore you would end up having that as your biggest distance there, the greatest distance. Okay, so this says, what does the acceleration graph look like for the car motion we were examining earlier? So these are both position and velocity graphs. And this kind of shows the same situation, only with an acceleration versus time graph. So again, in order to find acceleration of a velocity versus time graph, you would do the slope. Well, what's the slope of this right here? There's nothing, right? So it's just the 0 slope. And then it goes all the way down to this 0 velocity at this point. So it kind of does this little dip here. And then at 30 seconds, it kind of starts back, right? It starts back again. And then it has no slope again. And even though we have a negative velocity here, and this is at 50 seconds when that starts. So it's kind of slowing down again, but it just has this sort of constant no slope velocity. So it's 0 acceleration. This shows the speed of a car traveling on a local highway. So you've got a steep slope that indicates a rapid change in velocity, as we know, or a large acceleration. And then, of course, the horizontal line has zero slope and represents zero acceleration. So this is the velocity versus time, or speed versus time. Okay, so you've got this really big high slope, right? And then it just kind of is going this constant speed for like almost 5 minutes. And then what happens to the speed? It slows down. Now it's turning onto the highway. It's going really fast, constant speed. Speed gets lower because it's behind a slow truck. It's passing a truck. Goes back down a little bit. And then it decelerates all the way to the stoplight here to a 0 kilometers per hour. Okay. This shows how does the acceleration change for a sprinter. So you can see that from 0 to about 3-4 seconds. They have this sort of constant acceleration, but then what happens here? It kind of curves. Well, if you took a slope of that point right there versus this point right here, which one has the greater slope? Well, that one, right? That means at this point right here, it's starting to get slower. It's starting to decelerate. And then, of course, it's not accelerating right here. Does that mean that they're not moving? No, they're moving. They're just moving at a constant speed at that point. So this shows a velocity graph, and it says, is the acceleration of the object constant? Well, it's kind of like the same situation as the sprinter. You've got like this slope happening, this slope happening, this slope happening. So do you have a constant acceleration happening there? No. If it was a constant acceleration, it would look like this. Just a straight slope all the way through. But it's curved, so that means that it's not constant. Okay, I think I probably need to end the video there so that I'm not getting too long on the video, and then I'll do my last video over uniform